This is joint work with Gilles Blanchard, and he's in the back over there. Okay. So this is a talk about multi-class classification. I'll first review the standard setup for that problem and then talk about our work. So just to set some notation, PI will denote the class conditional distribution of X, given that the label is I. And so you have training data from each of your classes. Let's say an IID sample, and NI is the sample size from the ith class. So the goal in classification is obviously to design a good classifier. And there's various performance measures that you could use, and the particular one that you prefer isn't really important for us in this talk. So the work applies in any of these settings. The problem we're going to be thinking about is that of classification with label noise. And to represent label noise, we're going to use what we call a mutual contamination model. So you have data, L different training samples, and the difference is that now the ith sample is governed by a distribution pi tilde, which is not pi, the true class conditional distribution. Instead, it's a mixture of all of the class conditional distributions. So intuitively, if the label noise is low, then in the expression for pi tilde, the weight on pi will be large, and the others will be small. So the goals are still, the main goal is still to design a good classifier where, just keep in mind, performance is measured with respect to these true class conditional distributions. You could also look at the question of estimating these proportions or estimating these base distributions, the PIs. Okay, so we're trying to solve this problem in as general a way as we can, so by making minimal assumptions. So in particular, these pi ij's are unknown. They don't have any nice symmetry properties that might make the problem easier. And the PIs are unknown. They might overlap. So this is, when I say label noise, so the distributions can overlap, which itself creates some noise in classification, meaning the optimal classifier isn't perfect. Label noise is in addition to that. So there's when you think of label noise, you may think of a slightly different model, which I'll just state here briefly. So you can think of X and Y as being jointly distributed, and first you generate an IID realization from this joint distribution, and then you take the labels of every instance and you randomly reassign them according to some probabilities here, theta ij. So these theta ij's and our proportions pi ij, they're related by Bayes' rule. So you can think in terms of either of these models, but the one I presented first is more convenient for us. By the way, this is, notice that these conditional probabilities don't actually depend on the feature vector X. So this is not instance-dependent label noise, just label-dependent. So the motivation for this problem, for us, it came from a problem in nuclear particle classification, where the problem arises from the fact that it's not possible to acquire pure training samples of a particular type of particle because other particles are always present in the background radiation. So these kinds of contamination models have also been used in crowdsourcing to model unreliable labelers. You can think of this contamination model as a special case of topic modeling, where the number of documents is equal to the number of topics. And I'll say more about the connections to topic modeling a little later. One other distinction with topic modeling, in topic modeling, the distributions are discrete distributions on a finite vocabulary, and here we're allowing for general distributions. And finally, there's this problem of learning from partial labels, which is, if you're not familiar, that's multi-class classification, where each instance is assigned a subset of labels which is known to contain the true label. Okay, so you can also represent that in this with these mutual contamination models. And again, I'll say more on the connections to that problem at the end. So there's been a fair amount of theoretical work on classification with label noise, and I've tried to list most of those here. So people have looked at learning from positive and unlabeled examples, which can be thought of as one-sided label noise in the binary case. Co-training is based on a reduction to classification with label noise. There have been several works in the pack learning setting. There have been some negative results recently showing that certain standard algorithms are inconsistent in the presence of label noise. And then also recently, there have been people looking at how you adapt algorithms based on minimizing a surrogate loss when you have label noise. So as far as I'm aware, all of this theoretical work assumes L equals 2. Now, in our case, I don't know about these other papers, but in our case, going from binary to multi-class was non-trivial. So that's one distinction to previous work. Also, all of these previous works make one or more of the following assumptions. So they assume that P1 and P2 have non-overlapping support, so that the label is a deterministic function of the input. Or they assume something about some symmetry conditions on the label noise that actually make training on the contaminated data the right thing to do. Or they may just assume that these noise proportions are known. So we don't make any of those assumptions. Okay, so before I can tell you how we solve this problem, I need to tell you about another problem first. And so I'm going to introduce the problem and just mention our solution to it. It's the problem of what I'll call estimating maximum mixture proportions. Okay, so you can think of this as a standalone statistical estimation problem, and it's one that we need to talk about our work. So say you have a distribution F and then several distributions H1 to HM. So we define this quantity kappa star, which if you look at the expression for F, it says try to write F as a mixture of some distribution G and these given distributions HI. Okay. Then of all such representations, find the one for which the sum of the new i's is maximal. Okay, so that the I can't even see the laser over there. So that the sum of the new i's is as large as possible. And whatever that maximum sum is, let's call that kappa star. All right, so you can look at this picture. So imagine that this triangle is the space of all distributions. And so here's F, H1, and H2. We're basically trying to write F as a mixture of some convex combination of the H's and some other distribution, such that the weight on the H's is as large as possible, or such that the weight on G is as small as possible. In other words, G is as far away from F, intuitively, as possible. If the G achieving kappa star is unique, we will call that the residue of F with respect to H1 to HM. So one thing we do on the way to studying this mutual contamination model, we establish a universally consistent estimator, let's call that kappa hat, of this proportion. So it's based on random samples from each of these distributions, and as those sample sizes go to infinity, kappa hat converges to kappa star almost surely. And if these proportions nu 1 to nu m achieving kappa star are unique, those are also consistently estimated as a byproduct of kappa hat. All right, so if you want to know more about this problem and this estimator, you'll have to talk to us offline or read the paper, just for time constraints. Okay, so now we can talk about our main result, which is when is this mutually contaminated model identifiable? So we can write the model in a simple form as P tilde equals pi times P, where pi is an L by L matrix of these class proportions. And P, just think of P as a column vector of the distributions, the true class conditional distributions, and p tilde, a column vector of the contaminated distributions that we observe. So you can think of it as a kind of factorization problem, because we observe p tilde, can we recover pi and p? So here we're thinking about it in the infinite sample limit where we know p tilde. Okay, so our main result is this theorem, which says it gives sufficient conditions on when this recovery is possible. So I will define the two conditions. We have two conditions that together are sufficient. I'll define them in a couple of slides. So we say P1 to PL are jointly irreducible and pi is recoverable. If those are true, then for each class L, PL is the residue of PL tilde with respect to the remaining PJ tildes. Okay, so in other words, it's possible to write PL tilde as a mixture of PL and the remaining PJ tildes. And furthermore, this kappa L is kappa star. It's the largest possible sum of weights on the PJ tildes. All right, in addition, continuing the theorem statement, kappa L is less than 1, and the new LJ weights are unique. And then finally, we can actually express the elements of pi inverse in terms of these weights using these formulas. So these are the entries off the diagonal, and these are the diagonal entries. All right, so that's nice. Then we can apply this consistent estimator I mentioned on the previous slide. So in the empirical setting, when we have data, we can estimate this proportion kappa L. And since the new LJs are unique, we can also estimate those. And then finally, we can estimate pi inverse from these formulas. Right? And once you have pi inverse, conceptually you're done, because then you can then left multiply this equation by pi inverse and get P, and then you know the problem. So here's just a sketch of the intuition. So let's imagine that P1, P2, and P3 are these three black dots. So the observed distributions with the tildes, they're all convex combinations of these, so they live in this convex hull. And intuitively, when we do this maximum mixture proportion problem, the vertices of this triangle are the residues. Okay, so the theorem says basically that this picture is accurate, and that when you find these residues, they are the true class conditional distributions. So just a point, once we have pi or pi inverse, then we can solve for P. Again, you have to do this in an empirical setting, but it's more or less follow standard techniques in statistical learning theory to actually construct a consistent discrimination rule. So once again, for time constraints, I won't go over that. And the poster was this morning, so sorry you can't. I think it's still up, but anyway. Okay. So let me tell you about these two distributional assumptions that we define. The first is about the true class conditional distributions. So we say that they are jointly irreducible if one of these two conditions hold, and we show that these are equivalent conditions. The first one says, if you have a linear combination of the PIs equal to some distribution, then all of those weights must be non-negative. The second condition is a little more wordy, but it relates it back to kappa star. So if you take any subset of labels, which contain some but not all labels, take any distribution Q in the convex hull of the PIs indexed by capital I, and take some other distribution Q prime that's a mixture of the other PIs, then kappa star of Q prime is equal to 0. All right, so I don't know, that might take a while to sink in, but you can think of the first one if it's easier to think about. So in the case, thinking of the setting of topic modeling, whenever these distributions are discrete on a finite domain, this assumption is equivalent to the what's called the separability assumption in topic modeling, which is basically that there exists a word that is unique to each topic. Or in the more generally, there exists some region of your input space where the support of PI is non-zero, but all other PJs have zero support. Support does not include that region. All right, recoverability. So this is a condition on the mixing matrix pi. So first of all, just realize, well, let me denote by pi I, the ith row, that's an L, the nth row of capital pi. So note that pi L is a discrete distribution. And let's also, by way of notation, just introduce EL, this indicator vector on the nth entry. So pi is recoverable if one of the following three conditions hold, and we show that these are equivalent. The first condition is probably the most intuitive. So it says, for every class L, there exists a decomposition of pi L as a mixture of EL and pi L prime, where pi L prime is a convex combination of the other rows of the matrix. So you can think of that in terms of this picture. So if you look on the left, the lower left, pi 1 is in the convex hull of E1, pi 2, and pi 3, right? And the same is true of pi 2 and of pi 3. So in this case, the matrix is recoverable. On the right-hand side, that's not the case. Pi 1 is not in the convex hull of these 3 points, so the matrix is not recoverable. And intuitively, the one on the left is low noise, and the one on the right is high noise. So in the high noise setting, it's basically saying that the observed, with pi 1 being way over here, it's basically saying that the P1 tilde, the observed, the ones that are apparently labeled class 1, it's actually a mixture primarily of classes 2 and 3. There's not much of class 1 in there. The other two conditions, so condition B, pi is invertible, and pi inverse is a matrix with strictly positive diagonal entries and non-positive off-diagonal entries. So that's just kind of an interesting fact. Makes it easy to verify, given any pi matrix, whether it's recoverable. And then C, so remember these pi L's are distributions, they're discrete distributions, and so is EL. So for each L, the residue of pi L with respect to the remaining rows is EL, this indicator distribution. All right, so here's recoverability in the binary case. Just looks like this. You can easily check. It means the sum of these off-diagonal terms is less than 1. So this is actually a condition that's been looked at before by other authors in this binary setting. So it's good that it reduces to that. And this is just a particular model that guarantees recoverability. If all of these pi's are a mixture of their respective vertices and some common distribution, then recoverability is guaranteed. Okay, so let me just connect this back to topic modeling. Previous work on topic modeling, I'm not an expert on topic modeling, so if what I say is inaccurate, let me know. But my understanding is that previous work that establishes consistent estimation of the topics assumes not only that the number of words per document goes to infinity, but also the number of documents. And so in our setting, the number of documents is fixed. It's just equal to the number of topics. So we get consistent estimation of the topics without requiring the number of documents to go to infinity. Of course, at the same time, we make a stronger assumption. We make this recoverability assumption on the pi matrix. And then learning with partial labels I mentioned earlier, in we haven't really worked out the details of this connection, but let's suppose you have 3 classes, and each instance is labeled with a subset of 2 labels, one of which is the correct label and one of which is not. So, so let's call those subsets A, B, and C. Then you can represent this as a mutual contamination model, but the rows of this mixing matrix, pi A, pi B, and pi C, they lie on the boundaries of this simplex, and because of that, they don't satisfy the recoverability assumption. So you can't directly apply our theory. But what you can do is resample your observed distributions in such a way to get new distributions so that those new distributions do satisfy the recoverability assumption from which you can then apply our theory. So, okay, so let me just summarize the contributions. So one thing we do is we look at this problem of maximum mixing proportions, which seems like an interesting problem in its own right, and establish a universally consistent estimator. We introduce 2 sufficient conditions, joint irreducibility and recoverability for decontamination of mutually contaminated models. And then we also, as a byproduct of the first 2 bullets, you get consistent estimation of these mixing proportions. And then as a byproduct of that, you can get consistent discrimination rules, which I didn't talk about. Okay, so I'll stop there. Thank you.
Thank you for the talk. So I have some settings in which I have some knowledge about sort of the size of the pi i's. Would that help in any way? So would this help in conversions or anything?
It might help to know that it satisfies, that your pi matrix satisfies the recoverability condition. That's an interesting question. I haven't thought about that.
Let's thank Clayton again for the talk, and also all the speakers of this section.